Hi, I'm Mike Stanzik and this is Digital Electronics Classroom. Thanks for joining us today. In this video we're going to be talking about Ohm's Law Part 2, in which we took some data in the lab and now we're going to put that data into a graphing program, take a look at what that graph looks like, make a model from that graph data, and then talk a little bit more about that and analyze and process what Ohm's Law is and how we use it, where it comes from. Alright, let's get started. So right here what you see is a graphing tool called QuickGraph off of the Physics Aviary, and I'm going to go ahead and enter in our information. X is the thing that we've changed, but I want to put current on the x-axis, and we measured that in milliamps. And on the y-axis we'll put voltage, and that's going to be in volts. And this will give us a form that's a little bit easier to interpret. So let's just put in our values. 1.52 milliamps corresponded to 1.03 volts. And then you can see it start to build on the right hand side as we add in our data points. 2.05, and then we have 5.93 milliamps corresponds to 4.01 volts. We have 11.8 milliamps corresponds to 8.1 volts, and then we have 17.8 milliamps corresponding to 11.9 volts. And so there is all of our data, and I know it might be a little bit difficult to see those data points, but you can see they form a line. They look like they're pretty linear. So we're going to do a little curve fit here, and I'll make a linear curve fit so it looks just like that. Okay, and so now we have this linear curve fit with this linear expression that says y equals 0.6714 times x plus 0.03439. And one thing that I want to say is that our y-axis here is our y values, that's voltage, and our x values are current. So we're going to substitute in for voltage for y and current for x. But what does this y-intercept mean? What is this in this slope-intercept form of a line? What does the intercept mean? It means that when there's no current flowing through this, how much voltage should be applied? And we know from our basic understanding of electricity that if there is no current flowing through a device, then there's no voltage difference across it. So that point should be 0, 0. And so I'm going to go back, and instead of doing a linear fit here, I'm going to do a proportional fit, which will force that point to be 0, 0. And then we get this expression, that the voltage that we're measuring is equal to this value, 0.6742, multiplied by that current. Okay. So now I'm going to go into my whiteboard here and just do a little bit of kind of further explaining. So I brought that picture of that graph over into the whiteboard, and let's go ahead and continue to look at this Ohm's Law lab. Right, so we have this expression y is equal to 0.6742 times x. But y is just a mathematical expression. What is actually on the y-axis here? That's voltage. So I have voltage is equal to this number 0.6742 and then multiplied by my x-axis, and so that's current. Next thing I want to ask myself is, what are the units for this number 0.6742? And so we have volts on the y-axis. Remember, this is a slope value, right? So it's going to be y over x. So this here is a slope, which is equal to delta y over delta x. So we take the y units and the x units here. So the y units are volts, the x units are milliamps. So this is volts per milliamp. Okay. Now I don't like the fact that that milli is in there, and I want to remove it. And so to remove it, I have to multiply both the numerator and the denominator by 1,000. Multiplying the denominator by 1,000 will get rid of the milli, and then multiplying the numerator by 1,000, I can either put a kilo in the volts, or I can multiply this numerator number by 1,000, and that's what I'm going to do. So the voltage is actually 674.2, and that's volts per amp. So if I had 1,000 milliamps, I would have 1,000 times 0.6742, and so I get 674.2 times the current right here. Okay. Now, what does this value mean? Well, it means that if I give the slope here, for every little particular much I go over to the right, and let's change this to a different little color here. I think maybe a green would be nice. And so if I move over just a little bit to the right, I go up a bit as well. So every time I move over one to the right, I go up a certain amount. So 1 over up a certain amount. How much up do I go? I go up in value amount of 674.2, for on this graph 0.6742. Okay, and same way if we look on kind of the how much we move over to the right, if we go up a little bit, move over to the right. So this is that whole idea of what slope is. And so for every little increase in voltage that I get this much increase in current, or this is how much more increase in voltage I need to get that much increase in current. That's how we can interpret what that slope is meaning. So for instance, if I had something that was getting 6 milliamps, and it had a voltage of about 4 volts here, right? And so that would be sort of the corresponding voltage needed to push through 6 milliamps. So that's resisting a certain amount. We need 4 volts to push through 6 milliamps. Well, what if I had a different resistor? What if I had something that looked like more like something like this? If that was the graph that we got. And if that was the case, then to get 6 milliamps, I would have to push with 12 volts, which is a much larger number than that 4 volts. So I have to push more to get the same amount of current. And so we'd say that this has a higher resistance, higher R, and this one has a lower R, right? And so what do we change about these two graphs? What's changed about the two graphs? Well, we can see that the thing that's changed about them is their slopes. They're both lines, they both go through 0, but they have different slopes. And so this is where we get the idea that slope here is what we're going to call resistance. And it's going to have units of volts over amps, which we're going to call ohms. This is ohms. Okay? And so now this generates our general form of what our equation looks like. If this is a resistance value, then we get voltage is R times I, or the current here, or in its familiar form, V equals I times R. Or I can rearrange it as I equals V over R. And this is what we know of as Ohm's law. So Ohm's law comes from the data that we take on an element, and we say that, okay, for how much voltage is required to push through a certain amount of current, and if it requires more voltage to do that, then that thing that we're measuring has a greater resistance. And that's what this graph is telling us right here. Just so you know, in our data, the resistor that I used was a 680 ohm resistor. And as you can see, we have 674.2, so our data accurately reflects our value within the tolerance given for the manufacturer of that device. So we calculated or measured a 674.2 on a manufactured nominal value of 680, and I think that's pretty good. Okay, so that's our Ohm's law derivation, where it comes from our graph. I hope you found this valuable and interesting. I'm Mike Stanczyk with Digital Electronics Classroom. Thanks for watching. Be sure to subscribe, and as always, have a wonderful day.